So we've worked out the math for the damped-driven harmonic oscillator, and it's all here, the entire solution to this differential equation that's shown up here. And now we just have to interpret it. So keep in mind these equations. You can always reference these equations as we go on, but now I'm going to start doing a few visualizations to try to help you understand this picture. So shown here is a plot of that equation. So I've got here a bunch of options for all the different inputs. I can put in the initial position, spring constant, the damping parameter, the mass, the forcing amplitude, and the forcing frequency. And this is the equation that results. So you can see there, damping friction 0.65, that's B, and so that's the thing that shows up there in that ODE. Forcing amplitude 0.33, that's in newtons, so that's 0.33, that's F0, right? This one is B. Forcing frequency 2.4, that's omega D, and so there's a 2.4 there, that's omega D. So you can vary all of those different parameters in this simulation. And then what is plotted, this graph here, is the solution of the ODE. So this here is the solution of that ODE, which you can get by plotting those equations which I found on the previous slide. So this is a graph of what that mass is going to do as a function of time. Let me put it in motion. So here is a visualization that's plotting the position of the mass as a function of time. That green dot traversing that graph is exactly the position of that mass as a function of time. And you notice there's kind of two pieces to this graph. So there's this one here. This is the transient piece. You can see that the oscillations are kind of dying out. And then now when we're reaching to this point here, we're reaching a kind of steady state oscillation here. The mass is settling down into just a regular oscillation with some amplitude and some frequency. And for what I want to focus on now is I want to focus on this steady state. So we're going to focus now on this piece. I want to know, well, I just want to think a little bit more about what is the amplitude. So you can see that this oscillation, this steady state oscillation, has some amplitude, and I want to know what that amplitude is. And we already know it, we have a formula for it, but let's think a little bit more about what the formula is telling us. So let's focus on this steady state amplitude here. So this eventually settles down to some oscillation which has some amplitude, and this would be twice that amplitude because amplitude just goes from 0 to the maximum. And we have a formula for what this oscillation looks like. So this oscillation looks like xp, that's that particular solution, which is a cosine of omega dt minus delta. So the amplitude of this steady state oscillation is given by this formula, which we already worked out previously here. And let me try to give you some intuition of what this thing looks like. So if you plot here, what I'm going to plot is the amplitude of that steady state oscillation as a function of omega d. So imagine I change the driving frequency and I measure the amplitude of the resulting oscillations here. What you find out is if omega d is equal to 0, I have some point here which, by plugging omega d into this equals 0, I get f0 over m omega naught, some value there. And what you will find is that if I increase the driving frequency, if I increase the driving frequency, it goes up for a while, reaches a peak, and then will fall off to 0. And this peak occurs approximately around the value of omega 0. So this peak here is called a resonant peak. So the phenomenon of resonance is the fact that if I drive the system, I'm jostling the system pretty close to the frequency that it likes to oscillate at anyway, the oscillations will get big. So this is near where omega d is around omega naught. Now it's not exactly equal to omega naught, and that's one of your homework problems, is to show exactly where this peak is. But it's in the ballpark of omega 0. So that means that, like I say, think of pushing a child on a swing. The swing has a natural frequency, which is omega 0. And if you push at exactly the same frequency that the child is oscillating at, the oscillations will get big. That's resonance. I've got here a mass on a spring, and it's set up to have a natural frequency of 1 Hertz. So omega 0 is 2 pi. Its natural frequency is 1 Hertz. Now I'm going to start driving this thing with this mechanical driver shown there. And right now, the frequency at which I'm driving it is 0.5 Hertz. You can see that the amplitude, the oscillations are not very impressive. It's kind of pretty slow, not very big. Now I'm going to increase the driving frequency up to about 0.86. You can see the amplitude's getting a little bit bigger here. Now let's go pretty close to the natural frequency, omega 0. You can see the amplitude is getting quite large. This is up near this resonant peak here. So amplitude's getting big when I drive it at its natural frequency. If I go beyond that, so now I'm going to higher and higher frequencies, like 1.25, you see the amplitude is sort of getting smaller now. So now I'm kind of going down this way. And if I go even higher, up to 1.5 or even 2, you can see that that amplitude is getting smaller and smaller, and basically I'm not doing anything. So I only get the big oscillations if I'm oscillating it or driving the system at something close to its natural frequency, omega 0. So let me try to summarize this important topic, where we've been. We wrote down the ODE for a damped simple harmonic oscillator in the presence of a driving force, a periodic driving force. And we solved that ODE by finding the particular solution. And we found that the full solution has a transient piece, so a piece which dies out, that's the oscillations which are dying out, and a steady state piece. The steady state is the kind of interesting one. That's where eventually the oscillator settles down and reaches some kind of steady state. And it has some amplitude and some frequency. The frequency that it oscillates at is the driving frequency that you are pushing it with. But the amplitude depends on several things. It depends on the amplitude that you drive it with and the frequency you drive it with. And we found that if you're driving the system or oscillating it at the frequency that it likes to oscillate at or close to it, you get resonance. The oscillations get big. And the applications of this, there's just so many. So here are just some that I can come up with off the top of my head. There's engineering applications, like there's a famous bridge called the Tacoma Narrows Bridge, and I posted a video of this on D2L. The bridge had a natural frequency, and the wind was blowing, somehow was exciting this, was driving the system at very close to its natural frequency. And the oscillations of that bridge got really, really big, and the bridge collapsed. So that's something you have to think about if you're designing a building or a bridge or any kind of structure. Microwaves work the same way. Microwaves, the frequency of the microwaves that you use to heat up your food are designed to match the natural frequency of the oscillation of water molecules. So the water molecules have a natural frequency, and that's being jostled by the microwaves, and the oscillations get big, causes the food to heat up. Pushing a child on a swing is another one. And MRI, magnetic resonance imaging, is another kind of works on these same principles. So a really, really important topic, which is why I spent so much time on it. There's a lot of details in the math that you have to spend some time getting right, so make sure you go back over some of that, the difficult math, and then make sure you understand the importance of this topic before going forward.